Hey everyone, welcome back. We're starting our journey to learn about programming video games for the... Hey everyone, welcome back. We're going to begin our journey... Hey everyone, welcome back to our journey of developing games for the ZX Spectrum Next personal computer. Today we're going to be discussing something that I think is probably the most important subject that we can cover when it comes to learning to program, particularly if we're going to be using machine code or Z80 assembly language, or even BASIC for that matter. As you know, in this video series, we're going to be covering the entire subject of game development, not merely game programming, but the subject of this video in particular is, I think, probably the most critical subject to cover when it comes to starting our programming journey for developing games. We're going to be looking at bits and bytes, as well as the binary and hexadecimal counting systems. So let's get started. So first of all, let's talk about what is a bit and why is it important for us to know what a bit is and be familiar with it and be comfortable with it. Well, if you think about a computer and what's inside of a computer contains circuit boards, and the circuit boards inside of a computer are built using what's known as digital electronics. This is as opposed to analog electronics. So digital electronics uses voltages that can be either one of two voltage levels, typically either 0 volts or usually plus 5 volts. Now, we don't need to concern ourselves with the actual voltage levels being used on the circuit board inside a computer. But what's important for us to know is that since computers do use digital electronics, these digital signals, being either 0 volts or plus 5 volts, having one of two states, this relates directly to the subjects we're going to be covering today, in particular, bits. If you think about a computer circuit board having electronic circuit traces on it, which essentially equate to wires, if you want to think of it that way. If you think of a wire either having one of two voltage levels on it, either 0 volts or 5 volts, this can also be thought of as, let's say, a light switch in your home. A light switch can either be on or off. So just as a light switch can either be on or off, a circuit inside a computer that is a digital circuit can be of one of two voltage levels, either 0 volts or 5 volts, and you can think of that as being either off or on. And this relates directly to bits. So what is a bit? Well, bit is short for binary digit. So you can see already we're starting to get a hint of how important binary is going to be in our programming journey. So a binary digit is a digit that can have one of two possible levels, being either 0 or 1. So these two values that a binary bit can contain, either 0 or 1, they are known as the binary values, and the reason there's only two values that a binary digit can contain is because binary is what's known as a base 2 counting system, as opposed to decimal, which we use in our everyday lives, which is a base 10 counting system. As you know, our normal counting system, being decimal, since it is a base 10 counting system, uses 10 unique characters, ranging from the character 0 through the character 9, whereas binary, being a base 2 counting system, uses only 2 unique characters, either 0 or 1. Now, I'm not going to get into all the details and mathematics of exactly how that works, using bases and exponents and all that. You can research that if you're really interested, but as far as programming goes, it's not something that's really critical for us to know. But we will need to know and be very familiar with bits and bytes and exactly how they're used and how we can convert from binary values into other values such as decimal or hexadecimal. Now, we're going to be discussing hexadecimal a little bit later in this video, but just to give you a bit of a preview, hexadecimal is what's known as a base 16 counting system. So as we just discussed, since binary is a base 2 counting system, having two possible unique values of either 0 or 1, and decimal is a base 10 counting system, having 10 possible unique values, then if hexadecimal is known as a base 16 counting system, how many different unique values do you think each hexadecimal character could possibly have? Well, it makes sense that since it's a base 16 counting system, obviously it's going to have 16 possible unique different values for each character. In this case, we would use the letters A through F, where A would represent a decimal value of 10, B would represent a decimal value of 11, and so on and so forth up until you get to the letter F, which represents a decimal value of 15. So let's go back to binary and bits now. So as we just learned, a bit is short for binary digit, and a binary digit is a digit that can have one of two possible values, being either 0 or 1. And the reason we looked at the circuit board inside the computer at the beginning of this video is because those binary digits, or bits, having a value of either 0 or 1, directly relate to the electronic signals on the circuit board inside the computer. The digital circuits inside the computer can have one of two possible voltages, being either 0 volts or plus 5 volts, and these are represented literally in our programming as bits, as the values of either 0 or 1. So that is why it is important for us to be very familiar with bits and binary, because they relate directly to the electronic signals inside the computer. Now, in a future video, we're going to be taking a look at the internal architecture of the computer and how the signals get transferred between the different major components inside the computer. But for now, it's very important that we understand that bits directly relate to the digital electronic signals inside of a computer. So a bit can have one of two possible values, either 0 or 1. So that's pretty simple to understand. Now, let's take a look at bytes. So what is a byte? A byte is simply a collection of 8 bits strung together. And each individual bit in the byte can have, again, one of two possible values, either 0 or 1. And when I'm referring to bit values, these are binary values. So a value of a binary character would be either 0 or 1 in binary. Now, let's take a look at a byte, which is 8 bits stuck together. And what are the important things we need to know about bytes? Well, one thing we need to know about bytes is that when we're counting using binary, we always start from the right-hand bit. So the bit on the rightmost edge of the byte is the one we look at first. And this is what's known as the least significant bit. And why is it known as the least significant bit? Well, the reason it's known as the least significant bit, or LSB, is because of something we're going to be discussing directly ahead, which is how we determine the value of each bit within a byte, because that's going to be something that's important for us to know when we're converting binary values to decimal values. Okay, the emergency has passed, and let's get back to talking about bytes. So a byte, as we just discussed, is a string of 8 bits stuck together, and the rightmost bit is being known as the least significant bit because it has the smallest decimal value. And if we extrapolate that to the leftmost bit, we can probably guess that that would be known as the most significant bit because it would have the greatest or highest decimal value. So let's take a look at decimal values of bits within a byte. So how do we determine the decimal values of bits within a byte? Well, let's start with the rightmost bit, or the least significant bit. So the bit on the very right edge of a byte, which is known as the least significant bit, has a value of 1. So this is a decimal value of 1. So when the rightmost bit is turned on, or when it has a binary value of 1, it also has a decimal value of 1. And let's go over now to the bit just to the left of that. So the bit to the left of the rightmost bit would have a value that is twice the decimal value of the one to the right of it. So the rightmost bit, or the least significant bit, when it's turned on would have a decimal value of 1. And if we double that, the next bit over to the left, when it's turned on, would have a decimal value of 2. And if we double that, the bit to the left of that one would have a decimal value when it is turned on of 4. And we keep doubling these decimal values as we go on to the left doubling from 1 to 2 to 4 to 8 to 16 to 32 to 64 until we finally get up to the very leftmost bit, which would have a decimal value of 128. So if we add all of these values together, 1, 2, 4, 8, 16, 32, 64, and 128, we get a total value of 255 decimal. So that means a byte, which is 8 bits stuck together, can have a maximum possible decimal value when all the bits are turned on of 255 decimal, which means that a byte can contain potentially one of 256 unique values ranging from decimal 0 through decimal 255. So let's take an example to find out how we can convert a binary byte value into its equivalent decimal value. So let's take an example byte of, let's say, 00010011. And if we convert this value into its decimal values, we take each bit that is turned on and we record its equivalent decimal value. So the least significant bit could have a possible decimal value of 1, and you keep doubling that until you get to the leftmost bit, which is the most significant bit, which would have a decimal value of 128. And so you take all of the bits that are turned on within a byte, and you record those decimal equivalent values of those bits, and you simply add those decimal values together. And once you add those values together, you get the equivalent decimal value of the entire byte. So one final thing that we need to know about bytes is that each bit within a byte also has a number. Now, don't let this confuse you, because the number only refers to the position of the bit within the byte. So, for example, if you wanted to refer to a particular bit within a byte, let's say you're talking about some programming function, if maybe you're shifting bits or you're changing the bits, and you want to be able to refer to a particular bit within a byte, the way we do that is we give each bit within a byte its own number. So the bit on the very rightmost edge, which we now know is referred to as the least significant bit, that is known as bit 0. This has nothing to do with its binary value, its decimal value, or any other value. It's simply a reference that we can use to refer to that particular bit within the byte. So the rightmost bit is known as bit 0. The one to the left of that is known as bit 1. And we just simply count all the way to the leftmost bit, which is known as bit 7. So a byte contains 8 bits, ranging from bit number 0 through bit number 7. And again, don't let this confuse you. It's not equivalent to anything related to their binary values or decimal values or any values whatsoever. It has nothing to do with their values, but simply a reference that we use to refer to which bit we're talking about if we want to discuss a particular bit or make a note about a particular bit. For example, we might say bit 5 is now turned on, or bit 0 is now turned off, something like that. So although it's not used in any sort of calculations or manipulations, it is used as a reference for when you're programming. It's useful to be able to refer to the individual bits within a byte, which would be the rightmost bit, bit 0, through to the leftmost bit as bit 7. Now that we've discussed bits and bytes and binary, let's talk about hexadecimal. Well, since hexadecimal is the base 16 counting system, where each character can have one of 16 possible unique values, if you are now familiar with binary and you want to be able to count from 0 to 15 in binary, well, you need 4 bits in order to be able to do that. So if you have 4 bits that are all turned on and you convert that to a decimal value, 4 bits would have values of 1, 2, 4, and 8. And if you add those decimal values together, you get a value of 15. So we can see that if we use 4 binary digits, or 4 bits, we can have 16 possible unique values ranging from decimal 0 through decimal 15. And having 16 unique possible values is exactly what we need in a base 16 counting system, right? So since hexadecimal is the base 16 counting system, it needs to have 16 unique possible values for each digit. And we know that in hexadecimal, those unique values range from the character 0 through the character F. And that would equate to the equivalent binary value, if we're talking about nibbles, which have only 4 bits, of the value 0000 through 1111. So if we look at a binary nibble, which has 4 bits stuck together, they can have one of 16 possible unique values ranging from 0000 through 1111, and those values equate to the equivalent 16 decimal values ranging from decimal 0 through decimal 15, and those equate to the equivalent 16 possible unique hexadecimal values ranging from 0 through the character F. Since one nibble, which contains 4 bits, can have one of 16 possible unique values, that can equate to one hexadecimal character, which can also have one of 16 unique possible values ranging from 0 through F. Now, the last thing we need to know about hexadecimal for this video is how would we count using hexadecimal. If you think about the decimal counting system and how we count in our normal everyday lives using decimal, we start with a single character ranging from 0 through 9, and then we roll over to 10, which obviously uses 2 characters. So the next digit over to the left increases to a 1, and then we start over again with a 0 for the rightmost character. And that increases from 0 through 9, and then we increment the character to the left to a 2. So we get a value of 20 in decimal. And that's how we count in decimal. So how we count using all these 3 counting systems, binary, decimal, and hexadecimal, the way we do that is we take the rightmost character and we start at 0, and we increment that until it gets to its maximum value, and then we increment the character to the left of it, and we reset the rightmost character back down to 0. And we keep doing that for all the bits or characters in these 3 counting systems. We simply increment the rightmost character until it gets to its maximum value, and then we set it back down to 0, and we increment the value to the left of that. And when that one gets to its maximum value, we set that one to 0, and we increment the value of the character to the left of that one. Well, that's exactly the same way that we count in hexadecimal. So if we have, let's say, 2 hexadecimal characters, we start with the rightmost one, it starts at 0, and we increment it until it gets from 0 through F, and then after F, it goes back down to 0, and the character to the left of it increases to 1. And then we again start counting and incrementing the rightmost character, again from 0 through F, and then when that hits its maximum, we increment the character to the left up to 2, and then that goes on, incrementing so on and so forth in all 3 of these counting systems, whether we're counting in binary or decimal or hexadecimal. It works exactly the same way, with the only difference being how many characters are available for each digit within each counting system. And now we come to the exciting part of our video, which is the homework assignment. Now, if we've made it this far in our video, which we have, I think we should be very proud of ourselves because we have laid what I think is a good foundation for beginning to program in Z80 assembly language and machine code as well. So if you've understood everything that we've covered in these videos, then that's fantastic. But if you haven't, I'll give you a heads up right now that there's going to be a little pop quiz at the beginning of our next video. So if there's anything that's unclear to you, you may want to go back and just re-watch those sections of this video. Now, let's get to our homework assignments. Our first homework assignment will be converting some binary byte values into their equivalent decimal values. And remember, when we learned how to do this earlier on in the video, all we need to do in order to accomplish this is to convert each individual binary digit within the byte to its equivalent decimal values, and then we simply add up the decimal values of each individual bit within the byte. And that will give us the total decimal value of the entire byte. Now our next assignment will be converting some hexadecimal values into both their decimal and binary values. Now, in order to do this, just remember that hexadecimal is a base 16 counting system, so remember how many different values each hexadecimal digit can potentially have. So that could be a bit confusing once you get past the digit number 9 when you're looking at a hexadecimal digit. but remember that the characters A through F also have their special values, and you need to take that into account when you're converting these. Okay, now let's take a look at our final assignment number 3. So assignment number 3, we are going to be looking at actually a 2-byte exercise where we have 16 bits to work with. Now we know how to convert the bits in a byte into their equivalent decimal values, and that's when we're talking about a 1 byte that has 8 bits. But what if we're looking at 2 bytes that have 16 bits? Because it will be very common for us to be looking at 2-byte values when we're doing programming. So this shouldn't be very complicated for us. It's no more difficult than converting the bit values within a single byte. We're just simply continuing the way we do it. All we need to do is continue doubling the decimal values of the bits as we move along to the left until we get all of our values filled in under the high byte, which is the byte on the left-hand side of this diagram. Now those of us who are feeling particularly enthusiastic can go ahead and try this bonus challenge assignment, which is create a spreadsheet to automatically convert a binary byte into its equivalent decimal value. Now, if you're familiar with Excel spreadsheets or other spreadsheets, this should be quite simple for you. All we need to do again is to convert each individual bit within the byte to its equivalent decimal values and add those decimal values together to get our total decimal value of the entire byte. So let's give this bonus challenge assignment a try and see what we come up with. And in our next video, I'll show you my possible solution to this exercise, and we'll see how it compares to yours. Now, I have already uploaded my solution to this challenge exercise to the private SpriteWorks Facebook group for my Patreon subscribers, so anyone who has access to that group can go ahead and check it out there and download it and take a look. And remember, if you would like to support this channel by becoming a Patreon subscriber, feel free to head on over to patreon.com/SpriteWorks and check out the different subscription levels there. So that, in a nutshell, is a basic introduction to bits and bytes and binary and hexadecimal, and these concepts are going to be invaluable to us when doing any type of programming, particularly in machine code or Z80 assembly language. So thanks for watching, and we'll see you next time.